what we did before for dynamic programming, and the way I taught it in the past was I have an instance and the bird has some solution and she gives me some advice about the solution. And then I narrow it down to a smaller sub-instance that my friend solves. And I don't have a bird, so I try all her bird answers and take the best of the best. All right. And I took a lot of that discussion out and just narrowed it down to, as quick as possible, how do we get you to understand the example with the graph? Now what we're going to do is, first time I've done this, is we're going to look at other examples of computational problems, but instead of solving them on our own, we're going to reduce them to the graph example, the leveled graph with shortest path or longest path. And I think this will give you another way of thinking about these problems. And the more ways you have thinking about problems, the better. So that's, since we're trying to solve some problem, so we're going through life solving this problem, and we're going to think about it as following states of a graph. So these are just some pictures talking about traveling through life. And it's nice to travel with someone, so it's nice to have a partner in your test. All right, so, and this is just saying again, being able to look at the same problem at different levels of abstraction, and you know, whether you're looking at the neurons or whether you're looking at machine learning, right? And it's how to simplify out the key ideas. And so let's just have a review of some things that are important to me. This idea of a loop invariant, that we're in the middle of a computation at the moment, and we're not going to worry about the whole computation. We're just worrying about what's true now and how do we progress from there, right? You all know that. And also, we can be focusing on all these actions, but I prefer to focus on a landmark of what is true now. And from what is true now, we're now at this landmark, what action do we take next? Those in engineering don't know this maybe, but at this level, I think everybody should be able to say, here's a simple piece of code, and when we're at the top of the loop, then we're going to have some loop invariant true, which in this case might be, I know whether the length of the string I've read so far is 0, 1, 2, 3, or more. I know whether the number of ones read so far is even or odd. So you can think, what do I know at the top of the loop? And we can have a state for each of the things that you might know. Like if you're in this state here, then you know that the string so far is of length 2, and you know that the number of ones is even, versus here you know it's odd, right? So here we have meaningful names to the states, and then if I'm in this state, then I have actions that I can take. I read the next character, and if the next character is a 0, then the length gets 1 longer, but the number of ones doesn't flip from even or odd. While if I read a 1, then the number of ones flips from even to odd. Everybody kind of understand these kind of pictures? People in engineering,
Yeah.
How is this for you?
It's similar to FSMs, like very similar. It's the same thing, I think.
Same as what?
Like just normal, like finite state machines.
Yeah, it is.
Yeah,
it
it's
is.
the same
That's what
thing.
it is.
Yeah, it's the same thing.
Deterministic finite automata.
Yeah.
Right. So this is kind of what we're going to be building in to solve our problem. All right. So what I like to say is that the machine has a very small brain, right? We don't want to remember very much, because if you remember a lot, then you need a lot of states, right? So the name of the state I think of is everything that Pooh Bear knows, right? He knows that the string is a blank 2. He knows that the number of ones is even, right? So so what he knows is written on the blackboard, and what he knows is kind of the name of the state. So here's an example. I might be in the state with this name, and what does this state tell me? Well, it tells me I'm in line 39 of my code. It tells me that I have some variable who I know's value is 3, and I have some variable y whose value is 0, right? That's what I know. So it's the name of the state that I'm in. And then you can take an action, right? If I'm in the way you do transitions, delta says if I'm in this state and I read this character, then what state should I be in next? And if I'm in this state where I'm in line 39, and line 39 says take the value, take this value here and read it into y. That's what line 39 of the code does. Then what state should I be in next? Well, I should move past line 39 into line 40, and I shouldn't change the value of x, and the value of y should take on the value of 1. Everybody kind of follow that? So I like to think about computation. This is a transition from one state to another, right? And we want the number of states to be small. So for example, if the state is remembering R bits, I have R bits written on Pooh Bear's blackboard, I have R bits is the name of the state, then the number of such states, if I have all combinations, is 2 to the R, right? So that's a lot of states, which if we have to if we have to look at each of them, then that's a lot of work, right? So here, if our states are this, and we know that the code has lines 1 to 100, so line is somewhere between 1 and 100, and x has a value 0 through 4, and y has a value 0 through 4, then the number of different states, right, is the 100 times the 5 times the 5, right? Everybody buy that? Now, in our case, I'm naming this is called the finite automata, which means that the number of states is a constant independent of the input. And that's not completely true here. Here are our input, we might have more states depending on what our input is. We're also not going to have a deterministic machine. Our machine is going to be non-deterministic, but we'll get to that later. Now, sometimes Pooh Bear used to know things, and it's going to purposely forget. So, for example, if it forgot the value of these R bits, then the number of states goes down. I should have an example here. Let me grab this here, and let's see, where are we? Oh, I guess it's sort of tight in here, but you can imagine down here, say I'm in line 39, and there, what did I do? I read in the value of y, and I forgot the value of x, right? So here we had a lot of states depending on which value of x there are, and here I just forgot the value of x, so that decreased the number of states. Does that make sense? And so we're going to forget things about the past, like Pooh Bear might remember that he's hungry, but forget the details about when he ate and stuff. All he knows is kind of the end result. All right, so let's think about, I'm going to just make up some stupid computational problems so that we can talk about it in abstract generalizations. All right, so the input is going to be some collection of objects that, and the solution will be a decision about all of those objects, right? He might decide to eat the honey. He might decide to exercise, right? He has, I guess in all these ones, he's deciding to eat, and the value of this solution has a poor outcome, right? In these ones, he's deciding to exercise, and so he has a positive outcome, right? So what is the solution? It's the decision about all your objects, just like we did with, with greedy algorithms. And then once you have all of these decisions, you have the full solution. You can talk about how valuable, how good of a solution was that? Is it valuable? Is it costly? And we want to find the optimal, our goal is to find the optimal solution, right? So a DFA reads the input one at a time, and we're going to sort of be doing that. So you can imagine applications for DFAs, right? You enter characters one at a time, you move through this game, you process jobs one at a time, you look at your DNA one at a time, right? And one of the reasons that dynamic programming tends to be able to, a computational problem is more likely to have a dynamic programming algorithm if there's some innate order to the objects that they appear. So we can look at them one at a time without remembering so much about the past. Just like in greedy algorithms, right? We kind of move through them one at a time, making decisions about it with minimal information about the past, right? All right, so here,
Topological order, right?
Yeah, some kind of order, right? Okay. I mean, in the greedy algorithm, we went through the coins in an order, largest to 25 coins, quarters first, and then dimes. That was an order, and what we remembered was the sum of the coins we've taken so far. We didn't really need to remember the details of those coins. We just had to know how much more money do we need to make up.
Yeah, and it also indicates that there's no loops, right?
Well, the loop comes more from the time. We're going forward in time.
Yeah, okay.
Forward in, time is we're reading these inputs, we're making these objects, we're making decisions about them, and we're moving forward in time.
I meant cycles, but by loop, I meant cycle.
Yeah. I knew you meant
no cycles.
I knew you meant cycles. And the reason there aren't cycles is because we're moving forward in time. We're reading more and more of the objects.
Yeah, right. Got it.
Right. So here, the story is we get the first object, we make a decision about it, right? We get this, we get these objects one at a time, and we make stories about them. And in the middle of the computation, right, we've gotten some of the objects, we've made some of the stories, and we want to think about what our loop invariant is. Our loop invariant is going to say, what do we remember? What state are we in, right? So we want to say, what's the minimal that we need to remember about the past, because we want the number of states to be small. So here I just have this little guy here. Maybe he's in the front line and he knows everything about the past, right? So maybe he knows everything about the past, but he doesn't want to tell Pooh everything, because then we'll have too many states if Pooh remembers too much. So we just tell Pooh just enough so that Pooh can move forward in knowing the important things, right? Pooh might not need to know what mistakes he's made in the past, right? That's just a little joke. Anyway, all right, so what might we remember, right? We might remember every object that we've read in so far. Is that a problem? If we remember everything we've read in so far, then it's remembering all of that. And then the number of states will be the number of possible inputs. And we're going to have to eventually look at every state, right? So that would be an exponential number of states of our graph. And we can't remember all of that, right? Does that make sense? We want to only be remembering, have a polynomial of number of states. So in some ways, we only can remember a log amount of information, right? The log of this is the amount of information. All right, so you could also remember all the decisions you've made, right? On your blackboard. You can remember on your blackboard all of that information, but that will also, then the number of states is equal to the number of possible solutions, and that's too big. All right, so what's the minimal we need to remember if we're especially, if we want to have there be a sense of time, is in some ways all we have to remember is what time is it, right? So I'm going to remember, hey, I'm ready for the first object, or I'm ready for the second or the third or the fourth, right? So in some ways here, my state, all it's remembering is what time it is, i.e. how many input objects I've read so far. Does that make sense? We might later need to remember more than this, but this is sort of the minimal that we have to remember. All right, so our goal, of course, is to make a graph with nodes S and T. So S is our start node, and T is our finish node. Where do we start? Well, we start when we're ready for the first input, and we're at T, we're done when we've read in all of the inputs, right? So eventually we're going to form a table, and so the table is going to be, remember when we did dynamic programming for the shortest path algorithm, we have a table, and the table will be indexed. We'll have an entry in our table for every state that you might be in. So we want a short integer to name the state, and here in this case, the integer is simply the number which input you're ready for next, right? 1, 2, 3. Here I'm in state 1, 2, 3, 4, right? Everybody following this? All right, now we're going to need actions. All right, so Pooh Bear, as he moves from one state to another, he's going to take actions, right? So here's Pooh Bear. He's ready for the first object. He gets the first object, and he makes the decision to eat. And when he makes that decision, every action will correspond to an edge. So he decides going along this edge corresponds to deciding to eat, and he moves along that edge. And then he gets another object, and he decides to eat. And then he gets another object, and he decides to eat. And so he follows those objects, and in the process, the path he follows is the sequence of edges that he took, which tells him the solution that he has, right? But of course, Pooh Bear must have choices, or else it would be a dumb problem, right? He could also decide to exercise. So this dark blue edge is the healthy choice. He's decided to follow the dark blue edge and exercise. And so here are another thing he could do, another solution is at each step, he could take the healthy choice following the dark blue edges, and he would get a different solution, right? All right, so now, really, as you're going through life, at each point, Pooh Bear makes his decision, right? He could decide here he decides to take the healthy choice. So he's following the dark blue edge, right? And then he decides to eat. So he follows the light blue edge, right? And each point he can make whatever decision he wants to make, right? Everybody kind of follows that. This is the game of life. Every point he makes a decision how to what action to take, and that moves him from state to state. Are people kind of following this?
Yes.
Excellent. Now, note that the final solution returned by the algorithm corresponds to the path that he took, right? Remember, a solution is a sequence of actions or the sequence of decisions that he made, right? Here he had to decide, do I exercise or do I eat or do I exercise? And that's a choice. And that's he chooses which of those two actions to take. And then the solution completely corresponds to the path that he took, right? So we have that for every path, there's a possible solution. And for every possible solution, there's a path through the graph from S to T. Does that make sense? All right. Now, remember, we have different solutions are going to have different costs. All right. Each solution / path, remember, solutions and path corresponds to each other. And each one has to have a value, right? And our goal will be to find the optimal path. Our goal, which is the same as finding the optimal solution, right? So how do we assign costs or values to these solutions? Well, in some problems, this could be complicated, but in the problems, most of the problems that we are going to consider, it's really quite simple. What we're going to do is we're going to give a cost or a value or a weight to each action, to each edge, right? And then the cost of the path will be the sum of the weights along the edges, right? Remember, our goal is to bring this to look like SD connectivity, finding the shortest weighted path through the graph. So each of our solutions will have a cost to each of these actions, and we will sum them up. All right. So here, exercising has a large value, while eating is negative. There's a cost to eating, right? He gets fat. All right. So then that here we're just assigning positive values to, right here we have bad values to eating all the time, and positive values, big values, to exercising all the time, right? And so this path here is just going to be the sum of these choices made, and it's a kind of a medium solution. So he's mediumly happy, and it's a mediumly good solution. Everybody kind of buy that? And so now we're relating.
Sorry.
Yeah.
I have a question. Is there more constraints for this problem? Otherwise, we could just use greedy for this, right?
Yeah, this is a dumb problem. I'm just giving you a flavor. Clearly, okay. The optimal problem in this is exercise all the time. If you want to optimize that, we're going to have more nuances to the problem for it to be interesting.
Okay.
All right. So here we're talking about what's the game of how we proceed through life, and we're going to relate it to a graph, right? So the states that you might be in life relate to the nodes of the graph, and the actions that you take in your life will relate to the edges, and life gets sorted by what time it is, and that's why we have a leveled graph, and the action each action has a cost. So each edge has a weight, and each solution is corresponds to a path through the graph, and the cost of a solution is the sum of these weights, and it corresponds to the cost of a path, which is the sum of the weights in the path, right? And what is our goal? Is we want to find out how to best live our life, and what we do is we run dynamic programming to find the best path through this graph, right? Does that make sense? Right? And how do we do dynamic programming? Well, we assume that we have a little bird to tell us non-deterministically which way to go, and maybe we have a friend who tells us, who solves our problem and travels along with us, right? Everybody see those relations here?
Yeah.
All right, so what is a reduction? If you haven't done reductions already, we're going to be doing more reductions in when we're talking about non-determinism. But in reduction says that you have an algorithm for one problem. In this case, it's an algorithm for solving dynamic programming on level graphs. That's the algorithm we have. And I got a picture here of an oracle, because usually when you do reductions, you call this algorithm kind of the oracle that we're assuming exists, that we use as a black box. And our goal is to be smart, like Einstein. Our goal is to solve an algorithm for this Pooh Bear problem, right? And how do we, if you want to solve the Pooh Bear problem, then what comes into this algorithm is an input to the problem. And we translate that input into a leveled graph. And the dynamic programming finds us an optimal path to the leveled graph. And that tells us that, of course, the path indicates the sequence of actions taken, which gives us the answer to our problem. Everybody kind of following this?
Yes.
Excellent. And as we go through this, remember that the running time of the dynamic programming algorithm is proportional to the number of edges in the graph. So what we want to minimize is the number of edges. In fact, the nodes are the subinstances. So I often say the running time is the number of nodes times the number of bird answers. Number of bird answers is for each question how many different bird options there are, right? So that's the degree of each edge. But it boils down to the number of edges in your graph. All right. So in order to have a dynamic programming algorithm that works, we need what is called an optimal substructure, right? Remember when we were finding the shortest path from S to T, and the bird told us to take this last edge, then there was this subproblem, which is how to get from S to this earlier node, right? That's a substructure. And so what we're going to do, and this, as I said, this is important for solving dynamic programming algorithms, is there's going to be this edge in this graph, some action that when I'm in this state, I can take this action, which is going to either pay me or cost me 20. And the weight of this action cannot depend on how I got to this state, right? Remember, I'm following somehow I got to the state, but I don't remember how I got to the state. All I know is I'm in the state. And the action I take, the options I have from the state and what those actions will cost me can't depend on the past, can't depend on the future. And another thing is now we have these two subproblems. The one subproblem is how do I get from S to this node as cheaply as possible? And the second subproblem is how do I get from this node to T as cheaply as possible? And the other thing that's true is that these two problems are independent from each other. When I solve this problem, it has nothing to do with what I do in the future. And when I solve the future problem, it has nothing to do with what I do in the past. Everybody kind of buy that?
Yeah.
All right. So now we can ask the question, how does Pooh Bear locally decide what action to take? Now, in this case, it's a pretty silly thing because both actions go to the same, from the same state to the same state. So clearly you take the better of these two actions, right? So in this case, it's pretty, as a voice pointed out, this is a dumb problem, but I was just, drawing pictures. But in general, we're going to think about, we're not going to worry about, when we form the graph, we're not going to worry about how Pooh decides which action to take. I'm going to continue to think that I have a little bird who tells Pooh which way to go, right? That's just not our problem. Our problem is to form the graph. All right. So what we're going to do is, when I'm standing in this state, I'm going to think about asking a bird, well, what actions could I take now, and what would the cost of those actions be, right? So I can say here, if I'm in this state, what actions could I take? And the answers, the edges are going to be labeled with the actions. So here, I often index them by K, right? Action K could be eat, or the action K could be exercise, right? See, those are the two different actions we could take, and we form this whole graph. Everybody kind of buy this? All right. Now, a question often arises if you have a little bird who can tell you things. Why don't you ask the bird, if you're asking him questions, the question is, which action should I take? Or tell me something about the solution, or tell me something about the input, right? You can ask any questions you want. So why not just say, hey, bird, tell me the whole solution? Anybody know?
Because the cost is often exponential.
Because the number of answers is exponential, right?
Yeah.
We have to have an edge for every answer you could possibly give. And there are an exponential number of possible solutions. So that's too many answers. So too many edges, right? And you're basically doing the brute force algorithm. So this would be a fine algorithm in that it would work, but its running time would be exponential and you're doing the brute force. All right. So here's some philosophical questions. Suppose I'm building a graph, and do I want to have a lot of short edges, or do I want short edges or long edges, right? Here, if I take short edges, then it takes me a lot of edges to get from S to T. Is that a bad thing? It's a good question, right? It's a bad thing. I claim it's not a bad thing, right? Because we're not trying to optimize how many edges it takes to get from S to T, right? I don't care if I take lots of edges or a few edges, right? Actually, when we're trying to solve the problem, right, what we care about is the sum of the weights of the edges. So if you had lots of edges with small weights, then that wouldn't be a problem, right? So we don't, but another thing we do care about is the running time of our algorithm. The running time of our algorithm isn't the time to traverse this path. The running time of our algorithm is how long it takes us to find the optimal path, right? And the running time, remember, of dynamic programming is how many edges are there to search through, right? We want to have a small number of edges. So this looks bad because there are a lot of edges, but let's turn that around. Here, look at, this looks like long edge, this looks like we only have one edge, where here we have lots of edges. So one might think it's better to have this long edge, right? But anybody want to tell me why it's better to have short edges? Hard to understand, right? So if you have long edges, that means there are more places that you might go to, right? A long edge can take you here or here or here or here or here or here, right? So that's a lot of edges, right? In fact, here, if I have n nodes here, and I have an edge from each of them to each of them, right? From each I to each j, then that gives me order n squared edges, right? That's a lot of edges. While up here, if my edges only go from node I to I plus 1, then I only have n edges, right? So the purpose of this page is to motivate that this top picture is better than this bottom picture in terms of the running time of finding the optimal path, right? So it motivates us to have lots of atomic actions, right? Instead of having big complicated actions, we'll break those big complicated actions into a sequence of atomic actions. And the advantage of that, as illustrated by this picture, is that maybe we'll have fewer edges. Everybody kind of understand where we're going?